You get homework up there? Did it pop up or no? Nothing? No. All right, that's okay. It's probably better because I'll cover this stuff fresh. All right, last time we just sort of went through everything that had to do with wires, inductance, internal inductance, external inductance, resistance, high frequency effects, high frequency resistance, high frequency inductance, and capacitance, right? So we did all that for wires. Now, and we talked about components. Do y'all remember in general how components don't look like themselves at high frequency class? Do y'all remember? All right, now, what I'm going to do is I'm going to continue on with something I started. Now, please take good notes here and let me explain this. In the real EMC world, it's really important to have a good understanding of what the signal you're talking about really represents in the frequency domain. And that's done by spectral analyzers. And typically, I was telling you that almost everything today that involves electromagnetic interference and compatibility issues has to do with the clock pulses that are trapezoidal. Do you all remember that class? Now today I'm going to go a step further, but before I do, I have to bring you up to speed with one of the most common techniques I use to talk about things, and it's putting everything in terms of a form that can be thought of as a phasor in terms, you'll understand. Now, just work with me on this one. So I put up this. You don't have to write this down, just make sure you understand. I said x of t was equal to the summation from n equals minus infinity to infinity of c of n times e to the j n omega naught t. And this is for any periodic waveform, so it can be any periodic waveform. And if it, if you think about some of the common ones like this, if this was t, period would be t, this would be tau, and this would be x of t, it's periodic. It's equal to that. Now here's where you pay attention. We know that if you take derivatives, we can get Cn double prime and Cn, and we can always use the derivative method to extract the value of the Cn we want, right? One thing I didn't say, there's also an average value called C0, and that you can't get from the derivative. All right, so work with me here, and you don't need to write this, but watch. I'm going to expand this, and I'm going to say this is equal to the summation from n equals minus infinity to minus 1 of c of n e to the j n omega naught t plus C0 plus the summation of n goes from 1 to infinity of c of n e to the j n omega naught t. And I'm going to make a stipulation that C0 is equal to just 1 over t, the integral from 0 to t of x of t dt. And you know what C of n is, right? In general, I can say that C of n is equal to 1 over t, the integral, it can go from 0 to t, over any period of x of t times e to the minus j n omega naught t dt. If you want me to, I'll prove that for you. So that's the relationships. This is the exponential Fourier series. And the thing to remember is that value of C of n is easily gotten by the derivative method for most commonly observed waveforms of periodic. Most, not all. Understand, everybody? That's important. Now, what I do is I'm going to take this three things, and I'm going to condense this down into something that will be far more useful. But I have to make a point. When you take a look at C of n here, C of minus n would be equal to 1 over t, the integral of x of t from 0 to t. Because it's minus n, it would be e to the plus j n omega naught t dt. You all see what I'm doing here? Agreed? Now, this also is simply, you can think of C of n as some magnitude of C of n, e to the j phase angle of C of n. Does that make sense? Right? It's a complex number in general. It's got a magnitude and an angle, correct? This, notice, there's the angle, minus j and omega naught, right? That's the imaginary part. Well, when you do this, that's really C of n conjugated, or it's magnitude of C of n e to the minus j angle of C of n. So it's the same magnitude as the C of n above, only when it's negative, the angle gets a negative sign associated. You follow? This is important. You all understand that, class? Now, if I come back here and I say, here's what I'm going to do. instead of counting from minus infinity to minus 1, I'm going to count down from infinity to 1, but I'll put a minus sign there because that's the only place the angle that shows up. Do you all see that, class? X of t is, actually, let me do it this way. I can represent this as the summation, that's not quite true, of magnitude of c of n, then e to the j n omega naught t plus the phase angle of c of n. And that would be from n equals minus infinity to minus 1, plus c0, plus, and then it would be the summation of c of n magnitude, n equals 1 to infinity, times e to the j quantity n omega naught t plus the phase angle of c of n. So I've included the phase angle in this exponential term. Do you all see what I'm doing here, class? Now the reason I did it is, and some of you probably know this because you've had me, you probably know it and you do, because now what I can do is say that this is equal to C0 by itself, but what happens when you add these two things together? Well, I'm going to do one thing. Now I'm going to have this go from just 1 to infinity, and I'm going to put a minus sign there. Before I was counting with n minus, right? Now I make n plus, and I throw the negative sign up there. Do y'all see this, class? Everybody follow me what I'm up to? But why did I do that? It's a bigger question. Take a look at this, right? And take a look at this. The magnitude of c of n is the same on those, right? What happens when I add e to the minus j theta plus e to the plus j theta? What do I get? 2 cosine, don't I, class? You all see that? That's the reason I did it, because now I can say this is really equal to plus the summation from n equals 1 to infinity. I took an infinite series, broke it down to a semi-infinite series, and its magnitude is just 2 times the magnitude of c of n. Then it's going to have the argument of cosine of n omega naught t plus the phase angle of c of n. And that would be x of t. Now this is called the single-sided cosine series representation of the waveform. Are you with me, class? And you'll notice the constant here in front is now 2 times the magnitude of c of n, not just the magnitude of c of n. That's the important thing. Write that part down. If you don't, I put that up in OneNote. Do you all remember seeing this in OneNote at all? When you look through it, I know there's a lot of stuff in there that I put up, but this was the series part. Does anybody remember seeing this?
I think it was on that last homework you posted, right?
I put a bunch of stuff up on there, but this is one of the things. I'm just bringing it out in the open now, and I'm telling you why this is so important. And here's why it's so important. And I want you to really come to terms with this. This is the question I ask people, and sometimes they don't know how to do it. So suppose I have given this problem to you. I'm your potential boss. You're interviewing for a job, and I've got to make sure you're not clueless about fundamentals. They do this. So here's the first thing. I'm going to give you a problem. I'm going to say this is 10 times cosine of 120 pi t plus 30 degrees volts. That's a voltage source. And I'm going to put that in series with 10 ohms. And then I'm going to have an inductor down here. And the inductor is going to have a value of L equals, say, 20 millihenries. And I want the voltage here, plus the minus V out of T. So I want you to calculate that. Now, how would you go about doing that? Believe it or not, people fumble this one. Well, I'll give you one way. If you gave this to a person straight out of physics and math courses, they'd say I'd write a differential equation. Right? I would say this voltage is equal to the current I times 10, right? Plus L times di dt, right? So I'd have a differential equation. I'd solve for I, right? And then after I have I just multiply, take the derivative of that, multiply by L, and I got it. That's one way. That's a pain way. That's a painstaking way. You don't want to do that. How would you do it as electrical engineers?
Clause. You could use what clause?
Well, yeah, you could, but you just got out of circuits not too long ago, right? Right, well, there's a fundamental way. Isn't this represented in a phasor form? It's at a constant frequency. Can't we just represent this as 10 at an angle of 30 degrees and suppress the frequency component. Y'all remember this? This is important what I'm showing you. Now, I could also get rid of that. What do I replace that with? J omega L. What is omega? Carefully look. It's supposed to be 120 pi.
120 pi.
So 120 pi, right, times 20, right? That's 2400 pi, correct? But it's in milli, so it's 2400 milli, so it'd be what? 2.4 ohm, J 2.4 ohms, right? So this could be replaced by simply, am I right about that? 2.4 ohms. See if I'm right. Is that right? Well, sorry. That's 2.4 times pi. Can somebody do that for me? Take 120 and multiply it by 20 millihenries and just give me 120 pi. It's 120 pi. I want to do this problem, so hopefully this will stick with you.
125 times 20 million. 7.54.
Okay. So this is J 7.5 ohms, right? Do you agree with me? Now, what would the output voltage be here in terms of a phasor quantity?
Voltage divider.
Right. V phasor out would be what? Go ahead, say it. It would be
10 at an angle of 30 times J 7.5 over the sum of the resistance.
And let's do this. Do it with me. It'll stick with you. Over 10 plus J 7.5. And give this to me as a polar number because I want a magnitude and a phase. I'm not sure what that is, by the way.
So 0.6 at 53 degrees.
Could you check that, people? 0.6 at an angle of 53 degrees? I think that's right, but I'm not sure.
Sorry, I didn't.
I got 6.
I didn't multiply it by the voltage.
And the angle too, don't forget.
6 at an angle of 53.1 degrees.
6 at an angle of 53.1 degrees. All right? Now that's still not the time domain, right? But I'm your potential boss. I want the time domain. How do we bring it into the time domain? Here's where people, please watch this too. I want to make sure you see it. If you don't know, please watch. If you have something in the phasor domain, the tilde means phasor, and you want it in the time domain, you can say V of t in the time domain is the real part of simply the phasor times e to the j omega naught, or j omega t. Now the omega is the frequency that was suppressed, in this case 120 pi. But I want you to notice what happens here. V has a magnitude and a phase, right? This is just the phase, isn't it? So really you add that and you can say that V of t here is equal to the real part of magnitude of V phasor times e to the j quantity omega t plus the phase angle associated with the voltage. And you take the real part of that, right? Now, y'all remember this. If I have e to the j theta, that's cosine of theta plus j sine of theta. Y'all remember that? That's Euler's identity. That's one of three, right? Remember this. This is very important. So the real part is just the cosine, isn't it? Well, the real part of this would just be cosine of omega, which is 120 pi t, plus the phase angle, which happens to be 53.1 degrees. So we can say V of t now is 6, really there, and it's cosine of 120 pi t plus a phase angle of 53. And you know, this is the bad thing. We're mixing radians and degrees. We should probably put the 53 into radians, but I'm going to leave it as degrees now. 53.1 degrees. And that's V of t. Now that's how you got it. But what was the secret? You took a cosine representation with a frequency, an omega t, and a phase angle, and you wrote it as simple phasor term. You follow me, class? Now go here and take a look at this. Now we don't have just one term, but we have n terms, and we can represent these as phasors. Work with me on this one, because here's what I'm going to do now. I'm going to leave this circuit there, but now something's going to change. Now, what you told me with voltage division is this. You really told me if this is an X of T, and this is a Y of T out here, your output, this had some value H of omega. And what you did was, the way you did the problem, you took X of T and you put it in a phasor domain, or it becomes an X of omega at just one frequency, right? Then you took and found the output here, a Y of omega, by taking X of omega and multiplying it by H of omega. You evaluated the transfer function at the omega of the signal, the excitation frequency, correct, class? Well, what we can do is if we have an arbitrary periodic waveform that we represent like this, what we can do is say this is really in the phasor domain. If you take a look at its phasors, what is this in the phasor domain? This would really be not omega, but n omega naught, right? It would be n omega naught. Let me go ahead and just do this first. Now, first it would be C0, that's what's the frequency is 0, correct? Plus, and then it's phasor now, so it would be, the frequencies are suppressed, plus the summation from n equals 1 to infinity of 2 times magnitude of C of n e to the j phase angle of C of n. So now we can say this would be the x in the omega domain. Do you follow me on this? But each one of these is at a frequency of n omega naught, correct? Can you all see this? Everybody. If there was only one term, you would have only one phase. It would be like the 10 at 30 degrees term. Understand? But we have a whole bunch of terms and a whole bunch of different frequencies. So when we put this into any system, actually, let me just erase this. I want you to see this now. Remember, this is now in the phasor domain. Understand? The frequencies are suppressed. But now, if we put this into a system, if this was my x of omega, and I put it into, I'm using a block diagram here, a system where we knew the input-output relationships are related by x of omega, I could get y of omega by just multiplying x of omega by h of omega. And I think everybody can appreciate that. You all with me? Well, if I take this right here, and I multiply it by h of omega, please watch this. Now I get this. My y of omega becomes C0 times the transfer function h evaluated at 0 frequency. Do you all see that? That's the first part of the output. Plus the summation from n equals 1 to infinity of 2 times magnitude of C of n times e to the j phase angle of C of n, and now it's going to be that transfer function. And I'm going to put the transfer function in polar terms. So now it's going to be the magnitude of h of n omega naught. Remember, as n goes up, the frequency goes up, right? And it goes up in terms of the fundamental frequency. It's going to be n times the fundamental, which is omega naught. Understand, everyone, class? And this h of omega naught has a phase angle, so then it's going to be e to the j phase angle of h of n omega naught. Everybody with me on that? Now that's the output in a phasor form. And it's a series, right? And the reason I can do that is each one of these terms looks like a quantity can easily be put in terms of a phasor because it's a cosine form. That's the secret here. Everybody appreciate this right now? Now, what else happens? That's phasor. How do I get that to the time domain? What do? I erased it. But I would take that and then multiply it by e to the j, not omega, but e to the j n omega naught t, and take the real part of it. Do you all remember? Understand that, class? I would take this whole thing right here, and I'd multiply it by e to the j n omega naught t, because that frequency is the one I suppressed, right? And then I would take the real part. Do you know what it comes out to be? I'm sure you do. What happens in the time domain for original one? What happened to the output? It was in the form of a magnitude times cosine of what? Some omega t plus a phase angle, right? Same thing here. Now the output becomes this. My y of t becomes simply equal to C0 times h evaluated at 0 plus, please write this down, the summation from n equals 1 to infinity of 2 times magnitude of c of n times magnitude of h of n omega naught. Then it's going to be times cosine of n omega naught t, now catch this, plus the phase angle of c of n, right? So that changes with each value of n, but you have to add to this plus the phase angle of h of n omega naught. And I put these all in radians. And now you have the output. For any given system that's a linear time invariant system, like made up of resistors, inductors, capacitors, any linear elements, you have the output based on the input for any periodic waveform. It doesn't have to be a sine wave. It can be anything. I'm going to give you a MATLAB assignment about this for you to do and turn in for extra credit on Monday, all right? I want you to do this. This one I hope you appreciate, and I'll try to give you a template code. I did that before with you guys, and it's really useful to do this at least a couple of times to see the benefit. Now, when you have programs like you have PSpice, right, or LTSpice to use, right? LTSpice fundamentally is based on sinusoidal inputs or transient inputs, but there are ways to represent square wave inputs. Did you ever use a square wave input for anything? No?
Once or twice, maybe, not very much.
You can create I think you can create an arbitrary waveform. I say that cautiously because I actually haven't used LTSpice in years. But PSpice, all these spice things, these codes do that. And what they're really doing is this. We're going to write a MATLAB code that does this for us. All right? I mean, this is one of the things it does. It does circuit analysis very easily like this. Okay, guys? At least I think it does it this way. This is the typical way. And it's easy too. And that way you can plot a waveform, you can plot the output over a couple of periods, see what it looks like. All right. So now, which brings me back to my next point. Now we're going to take a look at the spectral energy what the frequency spectrum looks like for that trapezoidal wave I was starting to toy with. So please make sure you write this down, guys. I know it's Friday. I want to get out of here too. Is there any sporting event going on in Auburn this weekend? Or today?
It's kind of dead right now.
Let's say
Until football gets here.
everything's dead. Baseball's over, basketball hasn't started, neither is football. I don't know, is there any sport in the season right now? Tennis is
Major
fall.
League Baseball. No
Is
season.
is tennis spring or fall?
Yeah, that's going
I
on.
think it's both. Kind of.
Is it going
Maybe.
on now?
No, sir.
It's for college.
Yeah. Golf? Well,
Golf's over.
there's a tennis match right now going on between Federer and Nadal.
Yeah, I was gonna say Wimbledon's going on right now.
Yeah.
Federer was up 2-1 when I left the house. What's the score now? I wonder if I'm going to get in trouble for this. We just keep this between ourselves.
Let's see. Federer's up 2-1 and is up 1 in the
What's the score in the third, the fourth set?
fourth set, 5-4.
5-4. They're on serve probably. Is Nadal serving?
Let's see.
Could be a star by his name or an arrow or something.
I don't see one. That's what I'm trying to find out.
It's close. See, this
Freaking hard.
I think Federer is serving right now. If I'm reading this right.
what's that?
Federer is serving
Say
right now.
something hard.
I was saying tennis is so freaking hard.
Oh, it is.
I've tried it a couple
I
times.
played. My brother played for the Penn State team. He was ranked in Eastern regions. He wasn't so. He had heel spurs. He might have been pro, but I love playing tennis. But I tell you one thing: if you don't get somebody that knows what he's doing to show you how,
I mean, it can be fun, but it's hard to keep the ball down.
takes a while. It's like golf. Golf's a monster sport. Somebody that doesn't know how to play.
It's way easier than
It's
tennis.
way easier than tennis. It's also coming from a baseball background, though.
All right. Well, now at least I found out a sport that you're not jumping up and down to play, which is hard.
I've played it, I'm just not good at it, so.
All right. Now I'm going to swing the conversation back to what I should be talking about. But Hey, it's Friday, you know, one of these, sometimes you gotta just have a little fun. Sometimes, today's one of those days. And by the way, remind me to talk about the next test as soon as I'm done with this, all right? And I want the whole class to yell at me, make sure I don't forget it, because I'm prone to it with this kind of tennis pressure on me. I hope Federer wins. I like Nadal, but I, just for the, add one more to his collection. He's good. This is X of T. Now we're gonna go to the spectral energy. Remember that the actual tau goes from the centers here, right? And this is the rise time. And we're gonna use it as the fall time as well. And so that's my waveform, right? It's periodic, you all see that, correct? Now, that waveform obviously can be represented in terms of the exponential Fourier series. It can be represented as x of t equals the summation, 1 over t, the summation, and the integral. I can in this one go from 0 to, where n goes from minus infinity to infinity of c of n e to the j n omega naught t. And by the way, omega naught here is going to be simply 2 pi over t, in case you don't know. And that value of c of n, do y'all remember how we got that value of c of n? We did this one 2 lectures ago, I think. Do y'all remember that? What did I do? What's the secret? Derivatives.
Yeah.
We took one derivative, then second derivative, right? And we had 4 spikes, 4 delta functions. And I went and found what the value of Cn double prime was, right? And then I divided that by Jn omega naught squared. Do y'all remember?
Yes, sir.
All right, after all is said and done, I'm only caring about the magnitude. Please write this down. The magnitude of this, and you can look at your notes, is simply going to be A times tau over T. That's the duty cycle. Then it's going to be a sinc function, S-I-N-C, of n omega naught tau over 2 times a sinc function of n omega naught tau rise over 2. And I took magnitude, that way I got rid of that crazy phase thing, that e to the j omega naught tau over 2 plus omega naught tau rise over 2. Remember there was that phase term there? So I get rid of that by putting a magnitude. All right? Now, this is something I'm going to talk about in a second. But hold on. Now, what I would like, and I'm going to say this now, I'm not going to use this series. What I'm going to use is the actual value, or the actual cosine series. So now I can say that this waveform, x of t, will be equal to c naught plus the summation from n equals 1 to infinity of 2 times that magnitude, and that's 2 times tau over t, times the magnitude of the sinc of n omega naught tau over 2 times the magnitude of sinc of n omega naught tau rise over 2. You're going to have to bear with me to just get through here. And then it's going to be times the cosine, that times cosine of n omega naught t plus the phase angle of this quantity c of n that I don't even care about for this case. But that's, I put the c of n in there, right? And I've got 2 times that. Now, work with me on this. Yes, sir?
Where'd the A go?
What?
Does the A go away?
No, it doesn't go away. That's, I go away. See, this should be, you're absolutely right. As a matter of fact, you can actually take this series down to n equals 0 right here. Because the sinc of 0 is 1. And this you can count right there, all right? Everybody with me, class? Now, I want you to just appreciate something. At this point, This is the thing we worry about in the frequency domain. We want to take a look at that in the frequency domain. So that's what I was doing the last time, and I did a few things, or 2 lectures ago. What I did is, you don't have to write this down, just work with me and watch. Remember I said that omega naught is really equal to 2 pi f, right? Right, omega is 2 pi f. So what I did is I replaced these with pi f, f naught times tau, and this becomes pi f naught times tau rods. Do y'all remember that? F naught, omega naught, they're related by 2 pi, right? Then the next thing I did is say, I want to take a look, not at, I know the sync waveform is going to be doing this. I don't care about that, I want to see the envelope it's under. And so before I put that on, I've got to talk about a sync waveform in general one more time. If you actually take a look at the magnitude of a sync waveform, it's really the magnitude of sine of x over x, right? Well, it starts at 1. Then, as it goes by, it does this. It comes crashing down. First 0 is when sine x is, the first 0 is at pi, right? So at pi it goes down. Then if I go up here to 2 pi, that's another 0. Then 3 pi, another 0. And so forth. 4 pi, another 0. But the tips of this are all proportional. They're going down at a rate of 1 over x, if this is x. Are you with me? It's important you see this. Now that's important. And usually in electromagnetic compatibility analysis and in an EMI, electromagnetic interference analysis, what they always look is the envelopes, because that's the worst it's going to be, and that's what you always prepare for, the worst. Right? I mean, if you hit this null, if you're actually at this point, well, you don't have to worry about any signal, correct? But that's probably not likely. You're probably somewhere in this range, somewhere, not maybe at the peak, but not definitely to 0. So you always use the worst item. Now, when we're looking at this waveform, that's the sync function, right? Sine x over x, class. What we usually do is this. We turn it into a Bode plot type thing. When I look at a Bode plot in general, it's usually, not always, but it's usually 20 times the log of the function. In this case, the log of sine x over x, right? And then you plot versus x. That would be a Bode plot of the sync function. Sine x over x is Bode. That's sync. I wanted to do it this way to make sure you understand this. Now, you can approximate this. If you want to do a higher order approximation, just worry about worst cases, get rid of the sine. Because what does a sine function do? It's always between 0 and 1 magnitude. 0 and 1, 0 and 1. And by the way, when you do this, you're actually supposed to have a magnitude there for this thing, because it does go negative. Now, if you look at that, here's what happens. Right at 1 is going to be your break point where you start coming down, and the rate you're going to come down is going to be at 20 dB per decade. And the reason I got that is if I have 1 over x, right, this is equal to 20 times the log of 1 minus 20 times log of x, right? You all see that? Now just look at this for a second. What's the log of 1? 0, right? Log of 1 is 0, so I have minus 20x. Now just think to yourself, let's let x be 1. If x is 1, I have minus 20 log of 0, I have 0, right? So I start at 0. Now let x be 10. That's 1 order of magnitude, correct? From 1 to 10. When it's 10, log of 10 is 1. 1 times 20 is minus 20, right? It's minus 20. It's falling at 20 dB per decade. That's where that comes from. Follow me? And it's important that you appreciate this. Now, I'm going to go and talk about this function. But I want to make sure I covered that. So getting back to this thing, now I'm going to say I'll let n f naught go to a continuous frequency. And we know the actual frequency points for this periodic waveform will be some there'll be distinct places along this curve, right? If we just sweep versus frequency, NF naught appears at discrete points there, right? Watch me on this. So now I have C of N equal to A times tau over capital T, right? And then I'm going to use the approximation where I'm looking at worst case. So now I have really, well, I'll do it this way. I'll have the sinc of really pi f tau here, and then I'll have the sinc of pi f tau rise here. All right. Again, I'm replacing n f naught by f, just the continuous frequency. All right. Please watch this. This is important. But I really don't want C of n. If I'm looking at the signal spectrum, what I want is 2 times that, don't I? Because I'm in the cosine form. Do you understand this, class? Remember, there's a 2 there. So now I apply a 2. And that's really, you can call this C of n, I don't know, prime if you want, or star, something like that. But that's the C of n I want to see the signal spectrum of versus frequency. And I'm going to show you how this was plotted. This is a real important one to write down because we're going to be using this today. So now, when I take a look at just this and what it looks like, and we're going to do it in the standard way, we're going to do it in a really, this is the Bode way, it's going to be 20 times the log of the magnitude of C of n versus frequency, but the log axis would be used. So the way they do this usually is when they plot this, they're going to have 20 times the log of the magnitude of really of that C of 2 times magnitude of C of n here versus f. And remember, this is going to be a logarithmic scale, so this means it could be like 10 to the 5th, 10 to the 6th, 10 to the 7th, 10 to the 8th. So they can say the paper takes the log. The logarithmic increases are evenly spaced, right? Each order of magnitude. And then there would be those dashes, large dashes, they get smaller and smaller. You all know what I'm talking about with log paper, right? All right, now what does this actually look like? Well, if I take this right here, and I take, well, let me do it over here. I wish we had these pull-down boards that physics does, where they have 3 boards they can pull up and down. I love those. I watch these lectures at MIT, and I mean, a lot of MIT professors, unfortunately, have gone to the PowerPoint way, the evil PowerPoint. But a lot of them, especially guys and a physicist, they're pulling boards up and down, and I mean, they got a lot of them, and I like that. All right, now, when I take a look at that C of n star, if I take 20 times the log of that, its magnitude, you'll notice I have 2a times tau over t by itself, right? And I gotta say this, remember, log of a times b is log of a plus log of b. Correct, class? So what I'm going to do when I take 20 times the log of this, I'm going to take 20 times the log of this, then 20 times the log of this, and 20 times the log of this, and add them. So I've got that by itself. This is really 20 times the log of the magnitude of C of n star. Then I have plus 20 times the log here of the magnitude that's sinc, S-I-N-C of, and this becomes f, right, of pi times tau, and it's plus 20 times the log of magnitude of the sinc of f pi times tau rise. All right, now y'all realize that's a constant, right? That's it. I don't know what it is, but that's it. Do you all agree with that? So what happens is it's going to be a constant in the beginning. It's just going to be, this will be just 20 times the log of a magnitude of 2a and then tau over t. And that's it, it's where it starts. But you'll notice what this really looks like. This looks like a 1 over x if we're talking about the envelope, right? Sine, or sinc of x is sine x over x. Well, the sine, I said, can only have a magnitude of 1, and we look at the 1 over x. So this really looks like this. In terms of the magnitude we're interested in, it looks like 1 over pi f tau, right? And this really looks like the magnitude of 1 over pi f tau rise. Do you all see that, class? Right. Now, what happens with these is, and I'm just going to tell you, the sinc waveform, remember, for this value, when it's very small, I know 1 over that's very large, but the sinc of x, it starts, when x is 0, it starts at 1. It's never as greater than 1, and it starts monotonically decreasing. So what we do is, we say that this thing right here actually turns on when this becomes 1. And then for all other values, it's going, as it gets higher, it will start going down at 20 dB per decade, all right? That means, what frequency makes this 1? It's where f would be equal 1 over pi tau. Do you all see that? So you put a dash here, doesn't matter where it is. This is your first breakpoint, 1 over pi tau. And remember, this is the frequency domain, not omega. And that's the first break frequency. When you hit that point, now your waveform starts going down at minus 20 dB per decade. And it's going to keep going down at that rate until this one turns on. Tau rise is always smaller than tau. And that one turns on when what? When all of a sudden pi f tau rise is 1, or f is 1 over pi tau rise. So somewhere out here, you put down 1 over pi tau rise. And then when you hit that point, you start falling at minus 40 dB per decade. And what this is an envelope of the spectral, really envelope of the voltage in the spectral domain. Think of it that way. It's sort of, you know how Fourier series analysis gives you spectrum information, frequency domain information about time domain signals. What good is it? Well, if I've got a filter, if I have a signal and I take a look at this, and I know that my electronics are susceptible to things over a certain frequency, I can see how much of that spectrum is above there and kind of get a guesstimate of the effect on the electronics. And I can do that because up here, if I know this is my x of omega, think of it like that, if I know what my filter characteristics are, the system characteristics, my h of omega, I take everything up here and I multiply it by h of omega, and then I can see what kind of voltages or what kind of effects I'm dealing with. I want to give you a concrete example of this to see it working. And I also got to show you some tricks about how to do some calculations, so stay tuned. Don't tune out yet. If I have to, I'll give you the quiz on Monday. But now we have 2 full weeks together, right? Next week and following. And I asked you guys to tell me about the test, right? Have you any strong feelings when you'd like your next test? How about not so strong?
I think we were saying that Monday of the last week.
All right, that's the second test. All right,
Yeah.
so the not this Monday, the following Monday.
Yeah.
That would be great. All right, that's super. And then I don't know when our final exam is.
Wednesday the 31st.
Wednesday the 31st.
At 4 o'clock in the afternoon.
July 31st at 4 in the afternoon.
Yeah.
We may have to reschedule if we can get everybody in agreement.
Yeah.
I mean, if you're okay with it.
I have nothing.
Like for earlier or later?
Early.
Yeah.
In the day or in the week?
Earlier, both if possible.
Okay.
But it has to be unanimous, right? I can't do this. If there's one person that can't do it, I can't do it. All right, but this is something I'm gonna try to accommodate you and myself on this one. I don't wanna be here for it. And I'd rather not be here Wednesday, but you know, life is hard some days.
I don't think we have classes Monday or Tuesday. And there aren't any finals.
Wait, those are dead days?
Yep.
Well, let me think about
Does
something.
that change the test doesn't it?
Are you opposed to taking it on a study day?
No.
If anybody's opposed, you don't have to identify yourself, send me an email, you remain anonymous, because I can see a study day miracle happening if everybody is unanimously behind it.
Do we want Monday or Tuesday though?
Well, why don't you try to politic this out after class and then give me, because I'm working with you on this one, I don't wanna work against you, I'm trying to help you, not hurt you, alright? I wanna know when you want it. If everybody's in that. 4 o'clock's just not the time of day to do it. 2 o'clock, man, look at this class at 1:15 after lunch especially. I mean, sometimes it's, the looks that I see are amazing. Okay, now, here's a real example of how to use this. You might get an idea that I like this, and I do. This is the area. And you can make, I mean, not only that, it's interesting, challenging, financially very lucrative if you're in this area. This is compliance engineering. It's the end of the road design before the product goes out the door and makes money. And all the stuff is interesting to me. I like, if you're clever especially, you can do some amazing things. All right, so here's a typical problem. Suppose I'm given the spectrum of the input signal. It's definitely a trapezoid, I don't have to calculate it. I'm gonna start at 120, and it's dB microvolts. Now I didn't mention this, but usually when we talk about signals and we're plotting them and like in 20 dB log, it's usually dB microvolts. So let me explain this if you don't know it. A dB microvolt is really going to be equal to 20 times the log of an actual voltage divided by 10 to the minus 6. This is a scaling thing. A lot of times you're working with EMC signals really in tens of microvolts, sometimes hundreds of nanovolts, sometimes millivolts. So they try to scale them at 10 to the minus 6. This is dB microvolts. Follow me in this class? There's a similar thing you're going to see a lot of, and it's dB, and then it's M. This is dBm, and that's 10, not 20, times the log of a power divided by 10 to the minus third. dBm is probably something you've seen if you've had Dr. Wentworth's class in EMAG, right? There's also one other one that's common. It's dB microamps, and that's going to be 20 times the log of I over 10 to the minus 6. These are just common things you're going to see. dBm, dB microvolt, and dB microamp. And it depends on who's doing business. So I had an old flip phone and I could see the signal strength in my phone in dBm. I remember that. I used to be able to. I think your smartphones do it too, but I haven't messed around with any apps on my phone for that. So those are common things. Usually this is in dB microvolts, so it means you're taking that 2A times tau over T and dividing by 10 to the minus 6 before you take the log of it, all right? It's just scaling. You follow me on this class? All right, now it's going to stay there, and first break frequency is going to be at 10 to the 6. So write this down. This is 10 to the 6. And it's going to start going down at 20 dB per decade. Please write this problem down. It's a very good problem. And then out here at 20 megahertz, or 20 times 10 to the 6, it starts breaking at 40 dB per decade. Okay? And this is the signal. This is X. I'll call it the input. X right here of a mega spectrum. This is spectral energy, or spectral voltage, sorry. Now, this is going to go into a filter. So that's my X, my X of teeth, really. And it's going to go into a filter. And the filter has this property. Okay? Where's this? It does this. This is my output. Y of t or y of omega. And this is S of omega also. the filter starts at 10 to the 5th, and it's gonna go up. It starts at minus 30 dB, and it's gonna increase at plus 20 dB per decade. And this is my H of omega filter problem. So it starts at 10 to the 6th, and it's gonna keep going up, and it's minus 30 dB. I got 30 dB. It's a minus 30 dB. Okay? And what I want to know is, I want to know the output voltage. Really, I'm looking for the strength of the signal on the output at omega is equal to 50 times 10 to the 6th. So I'm looking out here, I want to know what Y is, the output. I want to know what Y is at a frequency of 50 times 10 to the 6th hertz. I'm looking at the voltage strength level out there, all right? Now this signal right here comes from a trapezoidal waveform. Everybody okay with that, class? I didn't bother drawing the trapezoid, then extracting these values because it's going to take too long. All right, but we can do that. It's easy to get. So how do you do this? Well, when I look at this whole thing, I can say my Y of omega, let me do it right here. I can say my Y right here is equal to X times my H, right? And I expressed omega, but we know the functions of omega, correct? Now, if I take a look at this for Y, I know I want my Y in terms of dB microvolts, so if I take 20 times the log of Y over 10 to the minus, well, actually, X is already in dB microvolts, so it's just 20 times the log of Y. That's going to be equal to times 20 times the log of X plus 20 times the log of H, right? Now here's the thing. I've already got H in terms of dB, okay? So I'm going to just extract a value for the frequency of 50 megahertz, all right? I've got to figure out what that value is and put it here for this. Now the log of X, if I look at this, I'm going to get it too. And I've got to get it at a frequency of 50 megahertz. So that's up here. That's 50 times 10 to the 6th. Please watch this. This is very important. You all see what I'm up to. Because this part right here is just finding out what this value is at 50 megahertz, right? That's the only thing we have to do. This is finding out what this value is when I'm out at 50 megahertz, right? So let me go ahead and do this. First one I'm going to do is the X. Now please write this down. Some people don't see this, but it's important that you get it. If I want to figure out what the value is out here at 50 megahertz, I don't know that. I start back here and I say my X at omega equals, not X, it's 20 times the log of X, but I'll say my 20 log of X over 10 to the minus 6 at omega is equal to 50 times 10 to the 6th hertz, radians per second. That's equal to, start there, that's 120, right? It started at 120, correct, class? Now watch this, this is important. At 10 to the 6th, it starts and it stops at 20 to the 6th, and it's dropping at a rate of 20 dB per decade, right? Now pay attention to this. So now I subtract minus 20 times the log at the frequency it stops, which is 20 times 10 to the 6th, divided by the frequency it starts, over 10 to the 6th. You always, if you're going to figure out how far down you go and you have dB per decade of fall off, you take 20 times the log of the upper frequency divided by the lower frequency where it starts. Where it stops at, where it starts at, understand? And just think if you went from 1 to 10 and there was a rate was 20 dB per decade, you would have 20 times the log of 10 over 1, right? it would be actually minus 20 times the log of 10 over 1, when the log of 10 is just 1, right? So minus 20. If it was from, if you started at 1 and you went to 100, it would be minus 20 times the log of 100 over 1, or 2, or minus 40 dB. If you're dropping 20 dB per decade, and you go 2 decades, 40 dB is what you should get. But if you're not going to stop at a decade, if it's an arbitrary value, then you take the upper frequency you stopped at and divide it by the frequency you started at, and that will give you in dB per decade. Or, I mean, that will give you the amount of dB you've actually fallen. All right, class? The 20 is the rate in dB per decade. So that's going to be really minus log of 20. Then you're going to have what? At this point, what happens? Now it's not falling at 20